Hello everybody, and welcome to our video on line integrals. Alright, so first let's figure out what we mean by a line integral. So we'll start by considering a plane curve C given by the parametric equations x equals x of t, y equals y of t, for t between a and b. This is equivalent to using a vector notation like this, r of t equals x of ti plus y of tj. And here we're assuming that C is a smooth curve, meaning this thing is continuously differentiable and all that. And the derivative is never equal to 0 as well. Okay, so here let's take a look at an example of a curve. So this looks like our graph for sine here. So if we divide this parameter interval from a to b, so from here to here, into a bunch of subintervals, t sub I minus 1, t sub I, and we let x sub I equal x of t sub I and y sub I equal y of t sub I, then the corresponding points p sub I, xi, yi, divide C into n subintervals with lengths delta S1, delta S2, so forth and so on, delta S sub n. So here, all we're really saying is that if we look at this picture, we can take and divide our interval from A to B into a bunch of pieces. And then if we look along the curve at each of those points, we can break this thing up into line segments that are just, straight lines. Okay, so we choose a sample point for each sub-arc, p sub I star, with a corresponding t sub I star. And now we'll consider f to be a function of two variables whose domain includes the curve C. We evaluate f at the point x sub I star, y sub I star, and multiply by the sub-arc length, delta S sub I, to form the sum from I equals 1 to n of f of x sub I star, y sub I star, times delta S sub I. Okay, so let's try to look at this in a picture and see what's going on here. So here we've got our three-dimensional image, and along this curve, this is our arc on the xy plane, or our path, right? So we've got our plane curve C, it's through xy, and then you've got this blue curve in the third dimension here that's going up and down, but it's moving along this path in the xy plane. It's just also going in the z direction. So this blue curve represents this function f and its behavior in particular above this black curve in the xy plane. So what this sum represents then is if we look along this curve and we break it up into a bunch of subintervals, we can approximate the area along each portion of the curve with rectangles, just like we do on a regular integral. Except here, what we see is it's like you've got a piece of paper curving through space and bending and twisting. And so we're cutting really small pieces out that look like little rectangles. And so that sum, the result of taking the limit of that sum, is what we call the line integral. And you can see physically it represents calculating the area of this, let's call it a sheet in 3 dimensions, right? So the sheet that goes along this curve in the xy plane and follows under this f of xy here. Okay, so let's formally define this. If f is defined on a smooth curve C given by the vector function r of t equals x of ti plus y of tj, then the line integral of f along C is the integral over C of f of xy ds, which is defined as the limit as the widths of our rectangles goes to 0 of the sum from 1 to n of f of x sub I star y sub I star times delta s sub I, provided that this limit exists. Now, of course, these Riemann sums can always be pretty difficult to evaluate, so we would like to be able to evaluate these using our regular theorems from Calc 1, Calc 2, and this class. So in a previous section, we found that the length of a curve is given by L equals the integral from a to b of this square root of dx dt squared plus dy dt squared dt. And you may recall that this is really representing the same thing as ds in this expression here, meaning each segment's little partial length, or delta s. All right, so it represents the same basic thing there. So that means if we want to find this integral of f of xy ds, we can instead use this evaluation formula for line integrals, which is to say that the integral over C of f of xy ds equals the integral from a to b of f of x of t y of t times the square root of dx dt squared plus dy dt squared times dt, where this curve x of t y of t is traversed exactly once as t increases from a to b. Now, one of the things that's mentioned here is the value of this integral does not depend on the parameterization of the curve, just like the length of a curve doesn't depend on how you parameterize it. When we're trying to find the area of this kind of figure, as we're looking at here, it's not going to change how you represent the curve. That's not going to change the area you calculate when you do this. Okay, so let's go ahead and tackle an example. Evaluate the integral over C of 2 plus x squared y ds, where C is the upper half of the unit circle. So if we've got the upper half of the unit circle, it's always sensible to just parameterize this in the usual way. So x equals cosine of t, y equals sine of t. Okay, so now let's go to set this integral up. Well, what do we know? We know that this integral is going to go from t from 0 to 1. Now we want to replace ds with the square root of dx dt squared plus dy dt squared dt. Sorry, I said t was going to go from 0 to 1. I meant to say 0 to pi. Try that again. Okay, but now we need to put everything in terms of t, right? If we leave things in terms of x and y, that's not going to make any sense. So we're integrating with respect to t here. So this gives us 2 plus, now for x squared, that's going to give us cosine squared of t, times y, but y here is sine of t. Now we need to know what dx dt and dy dt are, but those are pretty simple derivatives. Dx dt is going to be negative sine of t, and dy dt is going to be cosine of t. So this is going to give us negative sine of t squared plus cosine of t squared dt. Now, this is going to simplify to sine squared plus cosine squared, which is just 1. And the square root of 1 is 1, so we can rewrite this as the integral from 0 to pi of 2 plus cosine squared of t times sine of t. dt. And now I can split this into two integrals, the integral from 0 to pi of 2 dt plus the integral from 0 to pi of cosine squared of t times sine of t dt. This gives us 2t evaluated from 0 to pi. And then we're going to have to do a little u substitution here. So if we let u equal cosine of t, then du is going to be negative sine of t dt. So we'll get sine of t dt equals negative du. So this becomes minus the integral of u squared du. Now we have to change our bounds. So when t is 0, we get cosine of 0, which is 1. And then when t is pi, we get cosine of pi, which is negative 1. Now, this left integral here just is going to be 2 times pi minus 0, which is pi. So 2 pi. And then here I'm going to switch my bounds and make this positive. So this would be positive the integral from negative 1 to 1, u squared du. That's 2 pi plus u cubed over 3, evaluated from negative 1 to 1. All right, this ends up giving us 2 pi plus 2/3. All right, that's it for that one. So let's move on to example number 2 here. Evaluate the integral over c from 2x of 2x ds, where c consists of the arc c of the parabola y equals x squared from 0, 0 to 1, 1, followed by the vertical line segment c2 from 1, 1 to 1, 2. So actually, there's a little typo. This first one should be C1. There we go. Okay, so see, it consists of two arcs, C1 and C2. So let's kind of graph this and see what these look like. Okay, so C1 is just this parabola from 0, 0 to 1, 1. And then C2 is this vertical line segment going from 1, 1 to 1, 2. Now, we've got to figure out how to parameterize these curves. So let's just start with C1. C1's pretty straightforward. We can always set x equal to our parameter. So make this x equals t, in which case y equals t squared. And then just keep in mind we are going to need dx dt, which is 1, and dy dt, which is going to be 2t. And we also need to keep track of what our values of t will be. And so in this case, x goes from 0 to 1, and t is equal to x, so t goes from 0 to 1. Now for C2, if you remember, if you recall, we have a formula for finding parametric equations for a line between 2 points. But actually, in this case, because this is a vertical line, we can kind of figure one out just intuitively, I think. So x has to be 1 the whole time, so x is just the constant value 1. And y is going from 1 to 2. And it should be increasing. I would say we'd want to increase as t increases. So we want to start as t plus 1. And we want t to go from 0 to 1. So here, when t is 0, we get 1 for y. And when t is 1, we get 2. And that takes us from the point 1, 1 to 1, 2. Okay, so now, if we want to integrate over c, the key thing is we have to realize that we're starting on one path, and then we have to integrate along the other. So we actually have to integrate the sum of each path here. Okay, now for our second curve, just need to add in here that dx dt is 0 and dy dt is 1. So for our first curve, we get the integral from 0 to 1 of 2x, which is t, times ds, but ds is the square root of dx dt squared, so that's 1 squared, plus dy dt squared, which is 4t squared dt, plus the integral from 0 to 1 of 2 times x, which in this case is just 1, times the square root of dx dt squared, that's 0 squared, plus dy dt squared, which is 1 squared. All right, so just going to clean this up a little bit. All right, so here we're going to need a u substitution of 1 plus 4t squared. So du is going to be 8t dt. And I'd like to replace 2t dt, so I realize I can divide by 4 and get du over 4 equals 2t dt. So this becomes 1/4 the integral. Now, my bounds need to change, so when t is 0, I get 1 for u, and when t is 1, I get 5 for u. And here we should have the square root of u, which is the same thing as u to the 1/2 power, du. Plus, now this integral is pretty straightforward. I'm just going to get 2t evaluated from 0 to 1. Okay, so when I integrate this, I'm going to get u to the 3/2 divided by 3/2, which is the same thing as multiplying by 2/3. Evaluated from 1 to 5, plus 2 times 1 minus 0. This gives me 2 over 12, or 1 over 6, times 5 to the 3/2 minus 1, plus 2. This gives me 5 to the 3/2 over 6, minus 1/6, plus 2. 2 is 12/6, so this becomes plus 11 over 6. All right, well, that's it for example number 2. So let's go ahead and move on. Example number 3. A wire takes the shape of a semicircle, x squared plus y squared equals 1, where y is greater than or equal to 0, and the wire is thicker near its base than near the top. Find the center of mass of the wire if the linear density at any point is proportional to its distance from the line y equals 1. So the first thing is, what does it mean for the linear density to be proportional to its distance from the line y equals 1? Well, let's draw a little picture first. Okay, so this is our semicircle, and we're looking at the line y equals 1. And so the distance from y equals 1 to any point here is 1 minus the y value on the function. So this means our density function of xy is equal to a constant multiple of 1 minus y. Now, you may recall that in order to find our x bar, y bar, so our center of mass, x bar has to be found with the formula 1 over m times the integral. And in this case, we're looking at a line integral, so it's slightly different, but this is just a twist on the formula we've seen before. So in this case, it's the line integral of x times rho of xy ds. And our center of mass, or the y coordinate for our center of mass, would be 1 over m times the integral over c of y times rho of xy ds. But we can save ourselves some trouble, because since the density here is going to be the same regardless of which side of the y-axis you're on, we see that the symmetry of this problem is going to guarantee that our x-coordinate for our center of mass is on the y-axis. So we can actually just immediately recognize that x bar is equal to 0 here. But that doesn't solve the problem for y bar. Now, in order to evaluate y bar, we need to know the mass. And for that, we have to evaluate the integral of just the density function over the line. And of course, we're going to use the same parameterization that we usually use for a circle. So we're going to use cosine of t sine of t for x and y. So let's start out by rewriting this a little bit. This is the integral of k times 1 minus y ds. Now our integral is going to be from 0 to pi based on this parameterization. We can pull the constant k out in front. Now y in this parameterization is just sine of t. But then we need to multiply by ds, which is going to be dx dt squared plus dy dt squared, all under the square root and multiplied by dt. Okay, dx dt is going to be negative sine of t squared. Is going to cancel the negative and just give me sine squared of t, plus dy dt is going to be cosine of t squared. And of course, sine squared of t plus cosine squared of t is 1. So this just gives me 1 minus sine of t dt. Now the integral of sine is going to be negative cosine, so that's going to become positive cosine of t, evaluated from 0 to pi. This becomes pi plus cosine of pi, which is negative 1, minus 0, plus cosine of 0, which is 1. That gives us k times pi minus 2. Okay, so now to find y bar, we just need 1 over that mass times the integral of y times our rho function, which was k times 1 minus y, ds. And we can cancel the k here, which will make things a little bit easier. And we can also rewrite this as the integral over c of y minus y squared ds. Okay, y is sine of t, so we plug in sine of t minus sine squared of t times the square root of dx dt squared, which again gives us sine squared of t plus cosine squared of t dt. So again, this square root is going to just be equal to 1 in this case. So I can split this integral up. Well, I'm not going to split it up. What I'm going to do instead is start with my power reduction formula. So what's that going to give me? So I've got sine squared of t, so I'm going to have 1 minus cosine of 2t all over 2. All right, now I'm going to split up my integral into a few pieces here. Okay, the integral for sine of t is going to give us negative cosine of t evaluated from 0 to pi, minus 1/2 t evaluated from 0 to pi, plus sine of 2t divided by 2, and I've already got a 2 down there, so that's going to be divided by 4, evaluated from 0 to pi. Okay, cosine of t evaluated at pi is going to give us negative 1, and it's already negative, so that's going to be a positive 1, minus a negative cosine of 0. So now we've got minus 1/2 times pi minus 0, plus sine of 2 pi, which is 0, over 4, minus sine of 0, which is 0 over 4. This becomes 1 plus 1, which is 2, minus pi over 2. Okay, a little simplification brings us to 4 minus pi over 2 pi minus 4. So my center of mass is x bar y bar, which is 0, 4 minus pi over 2 pi minus 4. Okay, let's go ahead and move on. Now, we're going to consider a different situation, the line integral of f along a curve c with respect to x. So this is notated as the integral of c over c of f of xy dx equals the integral from a to b of f of x of t y of t times x prime of t dt. Similarly, the line integral of f along c with respect to y, same thing, except you've got dy, which changes to y prime of t dt. And sometimes line integrals with respect to t occur together in the following form: p of xy dx, the integral over c of p of xy dx plus the integral over c of q of xy dy, and we notate that as the integral of p of xy dx plus q of xy dy. So this may seem a little bit strange at the moment, but we'll see a situation where this arises where it makes a little bit more sense. That'll just be later on. Okay, so this is just a reminder. If you have a straight line segment from a point r0 to r1, a vector representation can be given as r of t equals 1 minus t times r0 plus t times r1 for t from 0 to 1. Okay, so example 4, evaluate the integral over c of y squared dx plus x dy, where a, c equals c1 is the line segment from -5, -3 to 0, 2. And b, c2 is the arc of the parabola x equals 4 minus y squared from -5, -3 to 0, 2. Okay, so for a, first we need to figure out a representation for our curve. Of course, this is a line segment, so we can just use r of t equals 1 minus t times r0, that's -5, -3, plus t times r1. This gives us here the vector -5 times 1 minus t. That's -5 plus 5t, and then -3, so that's -3 plus 3t, plus the vector t times 0, which is 0, and 2 times t, which is 2t. And now we sum those up, and we get the vector -5 plus 5t, and -3 plus 5t. And of course, this is for t between 0 and 1. All right, let's go ahead and set up this integral. So if I'm trying to do this type of integral with respect to x and y separately, then really I just need to treat this as a sum of two separate integrals. So in terms of actually evaluating, we're treating this like the sum of two separate intervals. Now we need to know a couple things. We need to know what dx dt is. So for this curve, dx dt is just going to be 5. dy dt is also going to be 5, right? So there's y, here's x. So the integral from 0 to 1 of y squared is going to give me -3 plus 5t squared times dx dt times dt plus the integral from 0 to 1 of -5 plus 5t times dy dt, which is 5, times dt. So just do a little cleanup here. Pull this 5 out in front. This will give me 9 minus 30t plus 25t squared. And for the second integral, I can actually factor out another 5 here with this 5 and put 25 in front. And then I'll just have negative 1 plus t inside my integral. All right, so let's go ahead and tackle integrating this thing. I made a silly mistake there. I had already divided by 2 when I integrated here to t squared. So I had 15, and then I wrote the 2 again for some reason. So let's fix that. So that should just be minus 15 times 1. Okay, almost done here. So we've got negative 6 is going to be negative 18 thirds plus 25 thirds is going to be 7 thirds. So 5 times 7 thirds is 35 thirds minus 25 halves. That's going to give me 70 over 6. Minus 75 over 6, which is negative 5 over 6. Okay, so that's it for part A. Now part B is going to be a little different. We need a different parameterization for our curve here. So here this curve is just the parabola, x equals 4 minus y squared. So the easiest thing to do here is to just set y equal to t. Then x is equal to 4 minus t squared, right? And t is going to traverse between, well, if y equals t, and y goes between negative 3 and 2, then t is going to go between negative 3 and 2 as well. Now dy dt is going to give us 1, and dx dt is going to give us negative 2t. So our integral here should be the integral from negative 3 to 2 of, and we should have y squared dx. So y squared, that's t squared, times dx dt, it's negative 2t, dt, plus. And now for our second integral, we should get x dy. So that's 4 minus t squared. And dy dt is 1, so times 1 times dt. Okay, so here we've just done our regular power rules for integration. And now we just need to evaluate at our bounds. So we're going to get what here? Okay, so t to the fourth, that's 2 to the fourth, minus negative 3 to the fourth. Plus, this is going to give me 4t, so t is 2 here, so that's going to be 8 minus 8/3 minus, and here we'll get a negative 12, and this will be a minus and a negative cubed, which is negative, so those will cancel. So it'll become plus 3 cubed over 3. Okay, so distribute this, we get a negative 2 cubed plus 3 to the fourth over 2 plus 8 is going to be 24/3 minus 8/3, so that's 16/3. And then this is going to be, so plus 12 and minus 9. Okay, so now we've got negative 5 is negative 30 over 6. These two added is going to give me 275 over 6. Okay, altogether that leaves me with 245 over 6. Barring any silly mistakes, which could happen. Okay, well, what's the big thing to notice here? We took two line integrals from the same point to one another, and we did not get the same thing at all. Got very different values for these line integrals. So keep that in mind, that the value of the line integral depends on both the specified curve and the orientation of that curve. In general, parameterization determines the orientation, so a positive orientation matches increasing t values. Now, a couple things to notice is that if you're taking a line integral with respect to x or y, if you change the curve to be oriented in the opposite direction, you will get the negative result for your integral. However, that's not going to happen if you're taking f of xy ds, because in the case of the full line integral with respect to s, this ds is strictly positive. Each delta s sub I is strictly positive, so you don't get that flipping of values. Okay, so let's go ahead and move on to line integrals in space. So for a curve C given by x, y, and z, all of t, with t between a and b, the line integral over c of f of x, y, z ds is the line integral from a to b of f of x of t, y of t, z of t times the square root of dx dt squared plus dy dt squared plus dz dt squared dt. So basically, it extends to the third dimension here in exactly the way you'd expect it to. So let's evaluate this line integral, and we've been given our parameterization and our values of t. So this one should be fairly straightforward. Our integral is going to be from 0 to 2 pi. X squared is going to give us t squared plus y squared, which is cosine squared of 2t, plus z squared, which is sine squared of 2t, times the square root. Dx dt is 1 squared plus dy dt is going to be negative 2 sine of 2t squared plus 2 times cosine of 2t squared when I take the derivative of z here with respect to t. Now we've got cosine squared of 2t plus sine squared of 2t. That's just 1, so plus 1 here. And here we've got 1 plus, and here I'm going to have 4 squared, or sorry, I'm going to have 4, 2 squared, which is 4. The negative is going to cancel, times each of these, so it's 4 times sine squared of 2t plus cosine squared of 2t. And of course, this is equal to 1. So this becomes the integral from 0 to 2 pi of t squared plus 1 times the square root of 1 plus 4, which is just the square root of 5. All right, this is a pretty straightforward integral from here. And when we evaluate at 0, that's just going to be 0. Okay, that's it for that example. Moving on. Line integrals of vector fields. So recall that the work done by a constant force F in moving an object from a point P to another point Q in space is given by work equals force dotted with distance, where the distance vector is the vector between P and Q. Suppose that F is given by Pi plus Qj plus Rk and is a continuous force field on R3. Let T of Ti be the unit tangent vector at a given point P sub I. So we can see that the force moving a particle from one point to the next is approximately the force multiplied by the length of the segment times this little tangent vector. So remember, our general definition here is work done on an object by a constant force, right? And moving in a straight line. So our simple definition was like, oh, it's just a little straight line. That obviously isn't going to work if the force is variable and you've got a curve through space. So what we're doing here is saying, take the force at an instant, at a tiny moment in time, and multiply it by the tiny piece of distance that you're traveling at that instant. So then, what does that tell us? Well, if we're dotting those two things, if we take a sum of the force dotted with each one of these components here, then that Riemann sum is going to lead us to an integral definition in the usual way, so that we get that work is the integral of F dotted with this unit tangent vector times ds. So work is the line integral with respect to arc length of the tangential component of the force. But we can actually simplify this expression a lot by noting that if C is given as a vector curve, then the tangential unit of component of the force is r prime of t divided by the magnitude of r prime of t. So if we substitute this in, then we rewrite f as f of rt instead of f of xyz, and we rewrite t as r prime of t over the magnitude of r prime of t, and ds is the magnitude of r prime of t dt. So this magnitude cancels, and instead we can think of work as being the dot product, the integral from a to b of the dot product of f of rt times r prime of t dt. And so we abbreviate this as the integral over c of f dot dr. Okay, so definition, let f be a continuous vector field defined on a smooth curve C given by a vector function r of t from a to b. Then the line integral of f along C is the integral over c of f dot dr, which is equal to the integral from a to b of f of rt dot r prime of t dt, which again can be written this way. So we're just summarizing what we just discussed. All right, let's go ahead and apply this to this example. Find the work done by the force field F equals x squared I minus xyj in moving a particle along the quarter circle on the path r of t equals cosine ti plus sine of tj for t from 0 to pi over 2. So this is the integral of f dot dr. Okay, so we need to find r prime of t. Well, the derivative of cosine is negative sine of t. The derivative of sine is cosine of t. We also need to rewrite f in terms of r of t. So f of r of t means we just substitute x and y from our path equation here. So we get cosine squared of t minus, well, for our second component, it should be minus cosine of t times sine of t. So this integral is the integral from 0 to pi over 2 of the vector cosine squared of t negative cosine of t sine of t dotted with negative sine of t cosine of t. Okay, so now we need to carry out this dot product, and we get negative sine of t times cosine squared of t for the first components. And then we get the same thing again, negative sine of t times cosine squared of t. So this gives us negative 2 sine of t cosine squared of t, but I'm actually going to rewrite this. Cosine squared of t times sine of t dt. So now we'll need to do a little u substitution. U equals cosine of t. So du equals negative sine of t dt. So negative du equals sine of t dt. Now I need to change my bounds. So when t is 0, I get cosine of 0 is 1. And when t is pi over 2, I get cosine of pi over 2 is 0. Putting that negative 2 out in front here. And then the rest of this is going to give me, well, I get negative du, so actually it'll cancel this negative. And then I'll get u squared du. This becomes 2 times u cubed over 3. Evaluated from 1 to 0, which is 2/3 times 0 minus 1, which is negative 2/3. Okay, so let's go ahead and just look at a note here real quick. So even though these force integrals are integrals, these work integrals, I should say, are integrals with respect to arc length, in this case, you actually can get that if you change the parameterization of your curve, you get the negative of your integral. And that's because the unit tangent vector would be replaced by its negative when c is replaced by negative of c, which should also align with if you think about if you're consider the gravitational force field, if you're moving up versus down, right? Like if you're going up, you're going against the movement of gravity, so you're moving opposite. So you would expect your sign for your work to be opposite of if you were moving down. All right, and finally, a fact. The integral over c of f dot dr is equal to the integral over c of p dx plus q dx plus r dz, where f is written as pi plus qj plus rk. So in other words, this is what connects line integrals of vector fields with those of scalar fields, and why we're concerned with integrating things of this form. Oh, that should be dy. That's a typo there. Please change that. P dx plus q dy plus r dz. Okay, that makes more sense. All right, well, that's it for this video. Thank you for watching.